So I wanted to go through, so there's a homework. So I just wanted to go through that. And then I haven't put the final up yet, but so when I put it up, I'll go through that on Thursday. It's just like all papers today and Thursday. Anyway, so let's see, let me open these up. Leave that. Look at these after, I guess. Well, it's this one too. So the homework asks about these two papers. It would ask about this paper by Saber and also this paper by Weissmuller. And I think that Saber, let's see, does he mention Weissmuller here? Yeah, he mentions Weissmuller like right at the beginning. So Weissmuller, so the idea is that you have, so Weissmuller is an earlier paper. The idea is you have like two metals, and it's going to make grains. So crystallize into grains as it's like a grain boundary. And one's it's an alloy, but there's only a small component of the black one, say. So these are like the Weissmuller says there's like three possibilities for this. Like you get phase separation, or you can have like some kind of miscibility where you have like domains of black, and then there's a gradient of the white. Or you can have a kind of immiscibility where the black can go to the interface, to the grain boundaries. Then the black can stabilize the grain boundaries. In that case, and Weissmuller says that there's like a thermodynamic driving force for that. See, and the idea is that people want to get small grains because of this Hall-Petch thing. So the yield strength. So again, you're going to have like you're going to do like stress strain and it's one here, that's what's all. That's like hooking elastic. And then at some point it yields. There's like a yield stress. And there's a modulus. It's like the stress over the strain. So the modulus, if you put small grains instead of one chunk of metal, make small grains, and the modulus drops. So the modulus drops somewhat, but the yield stress goes up a lot. So it would go like, so that in some cases that's a better material. Like it's a lower modulus, but it's got a higher yield. So this would be like kind of the failure, almost like the failure versus yield strain also would also be higher. So some desire to have these small, and this is the function that this Hall-Petch tells you how the yield strain increases, right? So the particle size, the grain size, D. Anyway, so that's one motivation. And then there's a couple other motivations to make, so in other words, nano grains. So I guess this is the Weissmullers from the 90s. In the 90s, everyone was doing nanoparticles, like mostly independent nanoparticles, like ceramics or even polymer nanoparticles, mostly ceramics. And then metals wanted to do nano too. So they started making nano grains. And it turned out there were some advantages to nano grains, having really small grains in the metal. I mean, so partly, I think in my mind, this was driven by funding. Like people wanted to put a proposal together on nano particles. And then and there was a bunch of federal money that went in the US into nano research. And metals was kind of left out because metals are like bulk, there is no nano to it usually. So the nano that they could find was the grain to get nano grains. And there's some advantages he also, I mean, historically, like reading it in that way, if you read this, like at the beginning, he says like, he talks about glass forming metals, which is another area of like making money, but it had no impact, right? So, and research money. So, and he says like, if you, he talks about glass forming metals in here and how this idea of like the alloying element going to the interface reduces the ability of the material to make glasses. So he's also talking a little bit about how you'd make a metallic glass, which also should have better properties, but basically, I don't think it's reached any kind of commercial application or actual use. So anyway, the idea is like, can you write, is this thermodynamics or is this kinetics? So that's the first thing that this Saber says. It's like, well, it could be kinetics. So for kinetics, he talks about Zener pinning, which is a lot like these oh, what's the name of it? Well, we had it's one of the other homeworks. We had like colloids and the particles go to the surface of the colloid. So it looks a lot like that. That's the name of that. But basically the Zener pinnings, the idea that if you have these domains and then you have a grain growth going on, so the grain front's like moving through, then it will like pin at these things. It'll get stuck at it as it grows through, and then it'll eventually reform, so that would be slowing down the kinetics of grain growth. And if you want to have nanograins, you want to slow it down. So then it's going to grow at a high temperature, and then you quench it down, it locks it in. So if you have these things like Zener pinning, so those are kinetic solute drag, porosity drag. So if you put pores in, the same thing happens. So basically you can somehow slow down the grain growth. So you start out, the grains would grow from nucleation site, then they grow. You want to get them to be like less than 500 nanometer, less than a half a micron, in order to get these effects like Hall patch to get a huge yield strength. Anyway, so there's a lot to do in this thing, like, and it overlaps with other, like, in other words, this kind of colloidal particle is very similar to these kind of, the topics overlap. In fact, one of the models is going to be like a Langmuir model for growth, right? Which is in here 14, and a Langmuir-MacLean segregation model, which is basically the Langmuir model, except applied to how particles, in other words, it's gonna, when these things go to the interface, you have an interface and you say it's going to be a monolayer, and then it will eventually reach saturation. So you'd have a curve like the excess at the interface versus concentration of whatever you put in is going to follow Langmuir. It'll look like that. Same as we got with the surface thing, like it'll peg out. Right? So because you fill the entire surface with these, you fill the entire interface with these particles. Right. So this Langmuir-MacLean thing is exactly the same as in colloids, except it's applied to metals. And in this case, metals copied colloids. Usually soft matter copies metals, but this is a case where the other's true. Langmuir is around the 1800s, and this is like 1950s, I think 60s or something. Anyway, so anyway, there's a lot to this, like different aspects to this homework that probably might find interesting, and you might not find interesting, depending on what you're interested in. So anyway, Weissmuller in 93, talking about like you have three possibilities: total immiscibility, and then partial miscibility. Then you can have this idea that something happens where these things can go to the interface. So, and then he's just talking about thermodynamics, right? So he's just saying like there's a thermodynamic, you can write a thermodynamic equation based on a regular solution model to move these particles to the interface. Right? So he comes up with a pretty simple model, the same regular solution stuff that we talked about, and then he goes through calculation, and he ends up that he can minimize the free energy expression for the system, and you can find that there's a magic grain size that he can get. So he finds a minimum of the free energy. That would be the magic grain size where it forms a metastable. Like the stable would be all black balls on the top, all white balls on the bottom. That would be equilibrium. So this is a metastable condition. It finds stability because there's some nuance to having the particles at the interface, right? And he can find that by a simple energy balance, and you can find that that exists. So that's 93, and then there's a bunch of other papers along these same lines. This is an isolated thing, right? So there's a lot of people studying grain growth, nanoparticle, nanograins, and this is an example of that, this North Carolina thing, right? So in the chapter, and I didn't go through in class, but in the chapter he talks about this surface excess is gamma, the excess at the interface. So that's from the surface chapter. There's a whole bunch of things about surface excess, and this gamma is the symbol they use for surface excess. In other words, when you have an interfacial concentration difference, then that gamma is like how much extra you have at the interface versus the bulk. Right? So that's a common thing. And then there's this is a Weissmuller, so he's repeating what's in that Weissmuller paper. So you have a surface excess, and then within the interfacial area, it has its own free energy. So enthalpy minus T delta S. And then gamma naught is without the interface, without the interfacial segregation. And then you can write these in terms of size and minimize it. Like he minimized it as a function of size, minimize the free energy as a function of size, and he found the minimum in this, which is the magic size. So then after 93, then people came along with the idea that when the particles are inside, there's a strain on the lattice, especially if you have mismatched atoms in the metal alloy. So basically, when you're in this case, so these things are strained in here, so it actually drives the black thing to the interface. That's strain. So the free energy can drive it to the interface, or this elastic strain can drive it to the interface. Right. So Weissmuller is missing that elastic strain part, and it turns out the elastic strain can be like the dominant feature. In fact, in this paper, he finds out the elastic strain is the dominant feature. At the end, he studies several systems, and he shows it for ones where there's a large mismatch between the atom size of the alloying atom metal and the matrix metal. Then there's a large strain in lattice, and that drives the particles to the interface. Then that stabilizes small grains. So you want to have a good mismatch between the sizes if you want to get nano grains, to get large yield stress. Right. So it's kind of a long story, but anyway, so there's no simulations in this, even though it seems to be like a simulation paper. It's just analytic calculations. So he's going to calculate like this, and this other group. So he ends up with two. WK is the one black coup idea. I think they add in the elastic, and the other one is this two. There's something S, the other one, and it's not Saber. It's in brackets. Oh, TS. Trelowitz and Shu, regular solution model. So TS is basically without the let's see, I don't remember what the difference is between these. It's a regular solution model for thermodynamic stabilization nanocrystalline, distinguish a grain boundary region from the grain interior region. Oh yeah, that's just so he's got instead of two regions, he's got three. He's got the bulk, which are the two sides, which have a solution. So he's got yellow and red. And he's got this grain boundary region is right along the center, I think, of this thing, where you have a different kind of bond set up. So each of these bonds has four coordination number Z of 4. Then when you get in here, these things have like less than 4 or more than 4. Like, well, they look like they have 4, but basically they have a different number of bonds in the middle. So that affects the free energy. And then there's also a region here. So this thing has a volume because it's got a thickness T. So you have the grains, which are size D, and then you have this volume of this interface. So you need to get he ends up getting this thing, which is the intergranular volume fraction. So you have the grains, so you have something like a grain. And you have this the inner granular is surrounded by something, other grains. Then there's this kind of weird shaped region, the inner granular region, the grain. And then he doesn't exactly define like what D is, but I think D is something like that, and this is T. So if he wants to get the fraction of inner granular, he calculates what's the fraction of D, I guess. So you could say like you have, well, he does it like this, D minus T over D would give you something like the fraction of granular. And he cubes it to make it volume. So this is kind of an odd equation because really it would be like the volume would be D cubed and this thing would be TD squared because it's the surface area times T and you divide by D cubed. This would be logical. D gives this, those are two different things for this FIG. He says like that's a granular, so 1 minus that would give you this FIG, right? So some kind of problem with this equation. You need to know what's a fraction of this inner granular. He's going to take the inner granular, he's going to calculate the free energy of the inner granular, and he's going to multiply it by that to get the fraction of it that contributes to the total. And then like 1 minus that would give you the fraction from the bulk. Like 1 minus FIB gives you the bulk. And then the fraction of the inner granular gives a total fraction. Right? So it's a volume fraction. Anyway, so some issue with this. If you go to 22, anyway, this is one of the homework questions, like derive equation 12, this FIG, and this isn't like a trivial question. The trivial answer would be like this. This is the thing he's using, they have the same thing. That's the issue. So where does he get that? So if you go back to his equation 12, he says go to 22, and 22 is reference 22 is this thing. So this is like totally useless when you look at it. So this is a question you're gonna have to figure out. And I think part of the answer is, so he's got like, this is the same equation, right? But he doesn't say where it comes from. He says it's based on a tetradecahedron having a thickness of blah, 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 blah. So you have to read this and figure it out. And then, so this 12 thing is not such an easy thing to do. That, and then this is what he references in this paper. He references this thing. He references page 211 or something. Anyway, I think it's page 211 because I said it in the header there. This Hillard thing. So this is a trip down, like, I don't know, it leads somewhere, but it's possible to solve this thing, but it's a lot messier than it looks like. So he just pops this equation out, and it's actually a lot more complicated than what it looks like. 12. This is just the geometry of whatever kind of hedron he's talking about, this tetrakaitis hedron. And he gives these, anyway, this is what the reference is to get to this. And then this is, he's referencing that to get to this, to get to 12. So anyway, it's a geometry issue, but it's kind of a complicated one. You may or may not be able to solve that. There's a question like, where did that come from? That's the root that seems to exist to get to where that comes from. Anyway, so other than that, it's just algebra using the regular solution model thing. So he's got that model, and he's going to add in an elastic energy. This is a segregation energy. This is an elastic energy. So it's got the modulus, the shear modulus, and the bulk modulus. I think you just have to believe that this is right. I mean, I didn't really look at the root of this thing, but anyway, this is a pretty common, like if you look at sorry. If you look at, or even if you look at that Langmuir segregation thing, wherever that is. Not this, not this, not that. I guess I didn't open it. Let's see. So if you look in this, they talk about at the bottom of this, they talk about elastic energy, right? The contribution. So this isn't something new. Energy of segregation, it's all the same thing. In other words, all these things are like the same basic thing. This is a Langmuir model for it, but they're all related to each other. So anyway, so yeah, this elastic energy isn't a unique term. Like he's using it here, but I don't exactly see what, I mean, the units work out. Like you have the modulus times the volume gives you this energy. But so in these, the units cancel out. So it gets like an average between the bulk and the shear modulus. Like a geometric mean between those with this 2 and 3, 3 and 4. I don't know what that's from, but basically it's something like a geometric mean modulus times the volume gives us elastic energy change, which the units work. So it's kind of in the equation kind of looks right. So I didn't bother to really look at that. Anyway, so it's going to be like add this chemical, which is from the Weissmuller, and then following that TS model through this equation, and then add it to the elastics. This is kind of what he's doing here. It's like summing these things up. And then after that, it's just a matter of using the regular solution model and just adding the things together. So alpha, so the problem is you don't know the energy. So the energy of an AA interaction, energy of BB interaction, energy of AB interaction. So we had that before from the interaction parameter. It'd be like that plus 2 times that divided by 2 gives you the average energy, right? AA plus BB plus 2AB divided by 2 gives you we did that in class. All right, so but then he uses the same, he doesn't have an energy for this intergranular. All right, he can get this, the cohesive energy density of the A crystal. He does that at the end. He gives 4 examples, right? So there's actually a paper that lists these EAAs. So you can find those numbers, but you can't find the interfacial EAA. You can only find the bulk. So to solve that problem, he invents this alpha, which is a fraction, the weighting fraction of the interface energy versus the bulk energy. And the idea is that the interface has a lower energy than the bulk energy. Alpha is always less than 1, which seems a little odd, but that's how this works. Right? So alpha is less than 1. When alpha equals 1, there's no difference between the interface and the bulk. So that means there's no energy contribution to the particles moving to the interface. I mean, it's only elastic. So when alpha goes to 1, it's just the elastic deformation of the matrix is driving the particles to the interface. Then you can also change another number to make the elastic deformation disappear. So he ends up with a long equation, but ends up being like alpha, and there's another number that changes, that you can pick what you want to look at. And then it's a mix of all these things. And he finds out an average number that would work for, anyway, so the energy of solution is going to be the bulk and then the interfacial. And alpha is governing the ratio of those things, the energy ratios of those. And then the reference is the bulk when you have pure A and pure B. So if you have a thermodynamically separated, A's on the bottom, B's on the top, there's no mixing, right? Then that's his reference one. So he has to subtract the solution one from the reference one. So it's algebra, right? And then he gets delta U from mixture. And so he's got kind of mixed notation here. N is the number of atoms, the total number of A atoms, total number of B atoms. And Z is the coordination numbers would be like 6 if it's a Cartesian coordinate. So he uses 6 anyway. So, and then B is NBAA is the number of AA bonds. So for every AA bond, there's 2 AA atoms. There's 2 times N number of bonds. And B is bulk here. So the nomenclature is confusing, right? NA totals the number of atoms, and NBAA is the number of bonds, even though they're both the same symbol. So if you want to understand this, you have to kind of resolve that in your mind. You don't necessarily have to understand that to do the homework, but basically there's a little problem with notation here. Anyway, so you can calculate the number of A atoms, or the number of coordinations of A, and then multiplied by the energy. So this would be like our Hildebrandt energy, right? EAB then minus EAA EBB over 2 gives it the energy difference for mixing. That's going to be like the chi parameter in polymers, the Hildebrandt parameter. So this whole thing's going to be omega here. Eventually calls that omega. Here, omega is that thing, right? That just the average energy. And then when you look at the interfacial part, it ends up being a little bit more complicated, so it doesn't have omega. It's got those things in it. And then he substituted in this fraction at the interface. So you'd have to balance that out. And then the total number of whatever component A or B is going to be like the bulk and the interface summed up. So, so everything's just an algebraic kind of manipulation of the thing. And then what else? The bonding probabilities, that's just the mole fractions. Like a mole fraction of finding A would be the bonding probability of A type thing. And the probabilities multiply, so ends up with these multiplied things. And then so you can read through this. I mean, he ends up with an equation, you know, that can describe, including the elastic and the regular solution model mixing free energy. And then he says the free energy, because there's no change, he assumes there's no change in volume, so the enthalpy is the same as the internal energy. And then he sums up the two internal energies from elastic and mixing. He gets the total enthalpy of mixing. And then that's it, like this mixing energy thing. Oh, and then he calculates the entropy too. This is just our normal X log X free energy thing, right? So he sums up those delta H minus T delta S to get the free energy, and then he's got a free energy expression. It's kind of equation 28. It's a gigantic equation, right? That's got entropy, enthalpy, elastic enthalpy, and mixing enthalpy for the two regions. Actually, three regions, like the interfacial and the bonding. So it's just an algebra exercise, right? And he ends up with this expression. He's added in the interfacial part. And then he's going to say, he's got these, I have this written down. So he ends up with his terms of interest. So he's got the bulk, XB is the atomic fraction of bulk, this capital XB. And then XIG is the atomic fraction of intergranular, and FIG is the intergranular volume fraction. So these are molar, and that's volumetric. And then he's got interfacial excess is gamma, which he said earlier. So that's like how much. So you have the amount in the two. There could be sum of A and B, and then there's amount excess at the interface. This only shows the excess, the last one, right? So, okay, so that's the idea. Gamma is the excess, and then capital X0 is the total mole fraction of like A or B. And then alpha is going to be the intergranular to bulk energy, like the ratio that says that the intergranular energy is lower than the bulk energy. So there's all these symbols. It would be really nice if he had put at the end, like in chemical engineering papers, they have a table of symbols that explains what everything is. Because I have like a page of all the symbols that he's using. I guess if you're going to look through this, I would suggest making that table so you have the table that he didn't provide, you know, of what everything was. Otherwise, it's kind of like he'll say like this depends on that, and you have no idea really exactly because he's inventing his own terms here. Anyway, so he's got this multi-differential, coupled differential equations with a constraint on it. Like he has to. This is just a mass balance of the system. That's his constraint condition. And he's got three differential equations, sec to the bulk atomic fraction, the intergranular atomic fraction, this FIG, the volumetric mixing of things between intergranular and bulk. So versus this guy just derived against the particle size. That's it. So this guy doesn't have the elastic. This well, what is his name? Wildebrand or something or other. What is his name? What Weissmuller? Weiss is white. Mueller, I guess, is like Miller. So White Miller. I think that's what it is. But anyway, so he just is going to have particle size of one parameter, and then when he gets to the minimization, he's just going to minimize against particle size, find the minimum, and that's it. That gives him the particle size that he wants, like how to make smaller grains and adjust the composition, do that minimization. So that's much simpler than this approach. So here he's got the atomic fraction, bulk, atomic fraction, intergranular. So this is a much more complicated thing, right? So one question is like, why is he doing it instead of just against the particle size? So I think partly it's because he's got like these other features in this. I mean, I guess you can count the parameters and it doesn't matter what you minimize against. Like if you have so many free parameters, and here he's got the elastic, and he's also got the thermodynamic, and then he's got something else. He's got that inner boundary layer where he has different bond numbers. So he's got three things that he's looking at that are different versus Weissmuller just has the one thing, right? So basically, because he has three things, he has to minimize against three, and it doesn't matter which three parameters he minimizes against. He needs three. So he picks three independent parameters, he minimizes against those. So these things and that thing all have to be true. So when you get in that situation, you reach into your mathematical bag of tricks and you find out that this is a Lagrange multiplier situation where you have like this is the link for Wikipedia's Lagrange multiplier, but you have some differential equation, you have the condition, which is his mass balance of the system. Then you want to find a solution and you can't do it analytically. Like you can't just plug in that thing and then find the answer because the equations are too complicated. So in that case, you resort to this Lagrangian function with a Lagrange multiplier constant, which you multiply by the constraint. Then you have this L, the Lagrange function, which is your function plus some number times the constraint function. They both depend on X. Then you do the derivatives. So you say that with respect to X has to equal 0 to find a minimum, and then you say that with respect to the multiplier has to equal 0. And those two conditions at the same time. If you do that, you find out that means that this whole function with respect to X equals 0, and that function has to equal 0, that's your original constraint anyway. So basically, that's the solution to this. So people don't, so yeah, you could analytically do that, right? But people don't do that. If they have such a complicated one, they go to this Maple program or some other program like it. What is it? MATLAB, not MATLAB. Mathematica will do this too. I think Mathematica grew out of this Maple, more or less. Mathematica will do this too. So you write your equations. This is his Maple. Maple originally was a shareware program like Mathematica, and it kind of got commercialized after. Maybe Mathematica bought it or something. Anyway, so he's using Maple. This is still available. So then you just these are just writing the equations out. Then you just tell it to use a Lagrange or you write it as a Lagrange multiplier equation, say solve it, and it gives the answer. Right, so this is the code that he used to solve those. So anyway, that's a nuance of this paper. So that's it. Then he finds the solution. He's going to find what this surface excess is, which is the intergranular composition minus the bulk composition divided by sigma, which is sigma is the surface area of the grains. So this is per area. So the excess per area. Anyway, that works out that gives you the surface excess. That's it. That's what he does. So parametric study means he's going to look at what happens if I change the things, change these things to get
to get different behavior for he's trying to get the smallest grain size he can at high temperatures. You're going to take this stuff, you're going to ball mill the two metals together. Then you're going to heat it up and anneal it at some high temperature. And typically the grains would grow. They would just keep growing to some large size. When you want to prevent that, you want to keep them at a small size. He's got a 20 nanometer grain. He wants to have it stay at 20 nanometer all the way through at highest temperature. So he mills it down here, then anneals it up here, and then quenches it. This is kinetics are kind of gone from this equilibrium. So in the alternative, in a kinetic model, you just say heat it up and quench it really fast before the grains could grow, right? And then you slow down the grain growth by putting in particles which do this blocking of the grain growth boundary as it flows through. But anyway, so this is changing. Omega is our Hildebrandt parameter, the mixing parameter. It's the same as our mixing parameter, right? And if you bring this to zero, you get like an equilibrium mixing. If it's negative, it favors mixing, and it's getting worse and worse as you go down. So as this arrow is let's see, increasing, more positive trend. So it's going towards a athermal system where you just have entropic mixing. Right. So it's not see, when that's negative, it's favoring mixing, and when it's positive, so it's demixing more as you drop this, increase this number, make it less negative. Right. So it's demixing more, so then you get more stabilization. It kind of makes sense. Like you have the second phase is being driven to the interface because it wants to get out because it's not mixing as well. Right. So it preferably goes to the interface. It's negative, so it normally mix, but because it's an elastic penalty, because it doesn't fit into the lattice, then it wants to go to the interface. So the elastic is what's driving it to the interface. That's what this is saying. The enthalpy is hurting here because it's the negative enthalpy of mixing. And then as you let's see, it's against temperature, and this is the interfacial excess. So how much goes to the interface? So as you make it less compatible, more of it goes to the interface. Like that kind of makes sense. So this like the first thing is kind of just a test. Does it make sense? I mean, all these are tests. Does it make sense? Or can you make sense of what it does? Again, this isn't a simulation. These are all calculations. So he plugs each one of these points into the Maple program. It spits out the answer, the grain size, and he puts in the temperature, and the grain size comes out. Right. So it's just a calculation he's doing. All right, then this is looking at the elastic. So how much elastic strain is there in the lattice? So as he reduces the elastic strain, so you have less driving force to drive it to the interface, then you get larger grains. So the particles, the atoms at the interface stabilize the nanostructure. And that shows that you want to have the highest possible elastic strain. Let's see. No, this is the opposite. So he's getting a lower elastic strain leads to worse conditions. A higher elastic strain would mean that you drive it to the interface, right? So you want to have the highest mismatch in size to make it, right? And the same, I think, goes here. Highest mismatch in size would be the highest elastic strain, and that gives you the larger interfacial excess, which stabilizes the particle size. So most of these things that you can explain. Effective global, so the amount of sol you put in. So this is like how much of this kind of dopant. So you don't really want this stuff in it, but you're going to put in some niobium or something expensive. And you want to have the least amount possible. So if you could get a low amount and get the stabilization, that would be good. So in this case, it's like 0.6. He gives a size mismatch in here somewhere of it. And then in terms of the interfacial excess, it doesn't make any difference, the mole fraction that you put in. So this is like he says this matches with the Langmuir-MacLean model, which means that you have this kind of, you're already working at a concentration you saturate the surface with a monolayer. It doesn't matter how much more you put in. You're in the pegged out part. If this part, so when you're over here, your surface isn't covered, and then the surface covers, and then it's flat. And so he's saying like putting more in beyond 0.02, it's already completely covered. It doesn't change it. Right, so that's his McLean, Langmuir-McLean model. And then this one, this is the one I think I asked about. I didn't really understand it. This is figure what? Figure 5. Figure 1, Weissmuller, figure 3. When I say figure 5 here, Sabre's 2, coordination number, G and D, and figure 5 of Sabre. Why does the grain size increase with temperature and why does it decrease with alpha? So generally, all of his curves, the grain size increase with temperature. That's because grain growth is, in other words, if it's set, well, kinetics speed up for one thing, right? So the grain size would grow just because it's kinetically faster, and if you wait a certain length of time, they'd be larger. Mobility increases with temperature. So these are all kinetic features with temperature. The kinetics are faster at higher temperatures, so you get bigger grains. Some kind of kinetic argument, I think, would go there. The other option is like the entropy is higher at higher grain size. I don't know if that works, but basically kinetics are faster. The alpha, though, is the ratio, so between intergranular and bulk energy. In other words, the intergranular energy is less than the bulk energy, and that drives the dispersed phase to the interface, which stabilizes the particles. So if you have a big difference here, you should get more particles going to the interface, and when it goes to 1, there's no difference between the interface and the bulk, the interfaceable energy and the bulk energy. So that means that there's no reason energetically why the atoms would go to the interface. So this doesn't seem to work, though. That kind of idea doesn't work here because at 1, you should have none at the interface, but that's where you get the most stable grains. So, and what he says about it doesn't make sense to me. So you're gonna have to figure out like why that is. This is figure 5, right? So interaction energy multiplier plays a role similar to that interaction energy parameter to omega in figure 2. That's true. It's the same as figure 2. Like you get, as this thing becomes more towards athermal, then you get more stable. So that there's no difference between the dispersed and no energetic difference between the dispersed phase and the matrix phase. That means the elastic energy just drives it. So maybe you can make the same argument here that when you remove the driving force to go to the interface, the elastic energy becomes dominant and that does it. But that doesn't, to me, that doesn't exactly make sense. But the arrow in figure 5 is an increasing more positive trend. Shows that when bond energies in the intergranular region approach their counterparts in the bulk, the nanoscale, he just says like the observation that the nanoscale becomes stable. Implies that segregation tendency is enhanced, but he doesn't say why. Like he never says like why. In fact, I can argue the opposite case. That's what maybe you look at it and see if you can figure out why. I don't have the answer to this one. This doesn't seem to make sense to me, the alpha thing. But the whole alpha thing, the definition of alpha might be important here. Like he isn't clear exactly what alpha means, like maybe you need to figure out what alpha means. So that's kind of a difficult. And then he gives some examples where he shows that this works, and basically mismatching size is the thing you want to make this elastic energy drive the things, which is something that he notes was already known before he wrote the paper. So anyway, it's kind of good because it goes through the this kind of regular solution model and shows an example of how to apply it, in a specialized case. So I think it's a good homework to do. Anyway, so that's about it for this. Then the first thing is like just derive it from the that's just, I want you to go back to the notes and just do whatever I did for let's see, this one. And then basically this guy, oops, that's not what I wanted. Here. Down, the first thing here is just derive it just go through these notes, like say you have the partition function. And if you get the free energy is KT times minus KT log of the partition function, then you automatically get the solution mixing term. And then if you mess around with that, you can get the whole regular solution free. Like if you go through this whole thing, just like I'm just asking you to go through the homework, go through the notes like that. Nanograms can explain kinetic. So just the kinetic is this tenor, the things he says at the beginning of the paper, right? Just what is the kinetic model for this? Like he says kind of right here, kinetic stabilization, Zener pinning. Zener pinning is the main thing that you can understand. You could look up those other, like solute dragging if you want. So there's reasons why you could think that it would be a kinetic situation. And also, like this, like I showed, the Langmuir can be, the Langmuir equation, where that is, the Langmuir equation can be derived from a kinetic approach or from a thermodynamic approach. So this McLean-Langmuir can be looked at from either way. So basically, you could use that argument too to talk about thermodynamics versus kinetics. The advantage of his model is that he can calculate. The kinetic model doesn't give you an answer. It just says quench it fast and you get small particles. I mean, you can get kind of the rate of phase separation. So it's not a cut and dry answer. Like basically the faster you quench, the smaller you get. Right. So that's not really an answer. Right. But the thermodynamic model can give you an answer like change this, put in more of the stuff, and then you get smaller particles. Or change the interaction energy between them and you get some different size particles. So there's knobs you can turn if you have a thermodynamic model. Kinetics is just like cool it fast. That's the only thing you have. Weissmuller figure 1 shows, so he shows this figure, so this is kind of the basis that he's citing for this work. So, and he's got 3 models. So how do these 3 models, 3 simple models, how do they fit in with this thing? So this is kind of like, I mean, it fits in, you know, this is showing the interfacial energy. This is showing like the mixing energy. So this one is basically if the things are 0, like some of the terms, like the elastic energy is 0 and some of the other stuff. So it's basically each one of these has a place in his model. You can kind of fit his equation. What's his equation? 12 or something? Omega equation. And his model is going to be this equation 28. So omegas are Hildebrandt interaction mixing parameter. Alpha is this segregation between the energy difference between the intergranular and bulk energies. Nu is what's nu? Nu's how much of a bond is in the intergranular. So nu has to do with this thing about they don't bond the same. Like when you get to the nu tells you that the bonds at this intergranular aren't the same number. So you don't have the same coordination number. Like it's 8 here, some other number here. Nu tells you what that is. So anyway, basically you have to 28, right? So you have to, there's all these parameters in here. Sigma is the surface area of the grains. These are the surface energies of the pure components. Alpha, this is the volume fraction at the intergranular versus the bulk, right? Elastic energy component. So this is just the entropy of mixing down here. So anyway, so what was this question? Anyway, the scenarios, like you can figure out from that equation, like which components of that correspond to each of these pictures. Just try to mix and match. Projection of solute leads to lattice strain could be relieved. Explain the origin of chemical advantage. So that's our mixing thing. That's a regular solution model. So explain the origin of the, just say, the origin of it is a regular solution model compared, so he's comparing the two between independent phases and the mixed phase. And then, so that's the origin of it. Derived equation 12, again, that's not going to be easy exactly. I mean, there's a simple answer like that, but that doesn't give you the answer that he has. And they aren't the same. Like, you can't work out algebraically that equals that. So then you have to look at those two papers. So Saber accounts for that with that parameter that I just said. So the answer to F I just gave. So what is it? This new number, I think, is the bonding in the inner granular, how the coordination number differs. To find that, you have to fish through this thing and find out the first place he uses new. He does define everything right before or right after he uses it, which is nice. Having it in a table would be pretty sweet. So you kind of have to make your own table, I guess. Let's see. New is here somewhere. So new is right here, to new. So that means it's before that. New is here. I don't see new here. New. The factor new is defined as the effective, so page 113, top right. Effective bond coordination contribution of the transitional bonding region in figure 1. Therefore, the total number of transitional bonds is new times the number of bonds you would normally have. Like the total number of atoms times their coordination number. And then the fraction that's in the inner granular times nu, which is a fudge factor. So I think nu ends up, I think he uses 1/2 in the end when he does the examples. Let's see, the examples are after that. It's before that. So at the beginning of these example things, nu equals 1/2. You're saying there's half as many bonds in the, it's one atom would have 8 on the normal bulk. And here it's going to have 4 when it's in the inner granular. So he just picks that number. Or I think he argues like why he uses that somewhere. Anyway, that's what, so this thing, F is new, and that's on 113 top right, and then you can look through what number he uses. G versus D, this is the thing about why you have to minimize against 3 things instead of minimizing against 1 like Weissmuller did. And then A to C equivalent state rather than just minimize with respect to the integrated volume. That's shown by Weissmuller. Is this really an equilibrium state? So it isn't, he even says all through it that it's a metastable. So it's like you're finding a metastable for it. Like it's got a crook in the free energy curve. It's not where it would totally be minimum in space. Minimum in space would be like they totally phase separate. Black on the top, white on the bottom. Purified is Saber. What does grain size? So I already mentioned that. So that's kind of it, I think, for today. Any questions on this thing? I mean, it's kind of like just an exercise and going through the regular solution model for this metal grain thing. People have worked on it quite a bit. I mean, so you can kind of see a few papers about it. But yep, that's it for today. I think I don't have anything else to go through. So on Thursday I'll do I'll put together the final and go through the 2 papers on Thursday. So Thursday will take longer. Right. Right.
You didn't complete grading homework 12, I have seen, but you said that missing question D. But question D is here.
Let me see. Yeah, no, yeah, but all right. No, you're missing, you can turn it in if you want. No, let me show you. This is homework 12, right? Or 12. So there's more than, it doesn't go to E, it goes to F. So you did A, B, C, and you called E, D, and F, E.
Oh,
Yeah, you missed D. So just do it if you want to turn it in.
yeah.
Yeah.
Okay, I'll turn it into the,
All right,
okay, thank you.
all right.
I didn't notice it.
Yeah, I know. You were the only one, but basically I knew what happened, because usually they're 5 and there's like
Yeah.
6 here. But this week there's more,
Yeah, till H,
this week there's actually, yeah, this goes further. This goes to H, yeah.
yeah.
There's a couple more, because this is just repeat the notes. I thought they didn't really count. And then, I don't know, I thought a couple of them were, there's a lot in this. I could have written more questions for this, you know?
Yeah.
I mean, actually, if you wanted to go through that other paper,
Yeah.
there's a lot you could do, actually. So anyway, I had to ask more questions about it.
Okay,
At least I felt that way.
I'll resubmit it to the.
All right, okay.